Alright, I'm doing my paper on modeling sonoluminescence, and it's by Alan Chodos and Sarah Groth. Before I get into what the actual paper is, it's important for me to define what sonoluminescence actually is. So sono meaning light, or sono meaning sound, and luminescence meaning light. Sonoluminescence is just turning sound into light. So light emissions are given off by sound energy. And it's so fascinating because sound needs a medium to go through and light does not. So the energy is actually changing form. So the way we can simulate sonoluminescence is pretty simple. It's just we need a flask of water. So if we have a flask that has water in it and we put an air bubble in the flask of water, also in this flask of water, if we submerge a speaker or something to give off a source of sound, and it gives off sound waves. These sound waves, they hit this air bubble, and the particles inside the air bubble get excited and they start heating up. And as a result, the bubble starts to give these sharp and short bursts of light. And it happens so quickly that it just looks like the light is just glowing, or the bubble is just glowing in the flask. So what the bubble is actually doing is when it gets excited, it begins to expand, and then it, in a cycle, it begins to expand and then it contracts. So with each contraction, the bubble emits a small pulse of light. Putting things into perspective, the sound given off by the speaker needs to be in the range of like 25 to 30 kilohertz. The best human has been able to hear about 22 kilohertz, and personally, I couldn't get past 15 kilohertz. This air bubble in here is very, very small, but when put under these sound waves, it gets very, very hot, easily at the point of 25,000 Kelvin. And there's been some speculation about it actually being nuclear fusion which creates the light. But the big question is, how does the light get created? Because we don't know how it actually gets created on the subatomic scale. So one explanation is by thermal radiation, which is just the sound waves make the particles in the air bubble get really excited. They move around really fast. They start to hit each other. They slow down. But because of conservation of energy, they have to emit photons. The other explanation is called vacuum radiation, which is what this paper focuses on. All right, so the main goal of the paper is to make a mathematical model of the light being emitted. So the first thing they want to do is use what is known of the physics of sonoluminescence to make an equation that gives the radiation as a function of time. So of the known physics, so if we have here on this side the radius of the bubble as a function of time. Look, the radius of the bubble looks like this. It grows gradually and then it drops slightly more steeply. And they want to find a function for that line. After that, they want to make a model that involves the electromagnetic field being coupled to the boundary of the bubble. And by doing this, there's an assumption that they're making. That assumption is that all of the radiation being emitted by the bubble takes place at the boundary. So if we have our bubble and it's being bombarded with these sound waves, all of the radiation is just at this boundary. Nothing is actually being emitted from within the bubble. So they use this assumption to say that the amount of radiation being emitted by the bubble could be measured by examining the electric and magnetic fields at this boundary. So those fields would also vary with the radius of the bubble, and then they would also, the two fields, the electric and magnetic field, would be able to be incorporated into a mathematical model that shows the amount of radiation given off by the bubble. So, continued in the second part.